Hello, everyone. Okay. I'm going to talk about our work on intrusion recovery for web applications. So we frequently hear of compromises in web applications. Even high-profile, well-maintained sites have had compromises in the past. For example, an attacker attacked MySpace.com, compromised and injected a piece of JavaScript code which influenced millions of users. And more recently, Twitter and Facebook have had similar attacks where attackers were able to modify other users' data, maybe change their profiles, and so on. Preventing these intrusions from happening is important, but prevention is not sufficient. These compromises will still continue to happen because vulnerabilities are common in web applications, and new web bugs are being constantly found. If you look at the CVE for the past 4 years, we find that on average there are about 3 to 4 new vulnerabilities being found per day. And even if we consider the applications are completely bug-free, administrators can still misconfigure security policies and making them too lax, giving opportunities for attackers to attack this web application server, say a wiki server, which does not sanitize its input properly. So an attacker, Eve, can compromise the server by sending a piece of JavaScript code inside a request. The server does not sanitize the input properly and inserts it into the database. At a later time, legitimate user Alice can request the same page, and the server inserts this JavaScript code into the response. Now, with the result that the Eve's code is running inside Alice's browser as Alice and making requests as Alice, perhaps giving Eve permission to all of Alice's files. While this attack is going on, Alice could still be browsing the site, and as a result of which, Alice's browser could be making other legitimate requests. Recovering from a compromise like this is pretty hard because web applications have many users, and they store all these users' data in a shared data store like a database. And users share data with each other, access each other's data, and so an attack can propagate across users and can arbitrarily corrupt user data. Moreover, attacks can install backdoors, giving attackers future access to the web application, say by adding the attacker to access control lists or installing a script that runs at a later point of time. So all these dependencies make it very hard to trace down the effects of an attack and recover from it. Administrators today have very few tools to help them with this recovery problem. Administrators can use a backup and restore tool to restore the state of the system to before when the attack happened. But if an attack was discovered several weeks down the line, then this restoration process will throw away all users' changes, including users who were not affected by the attack. Another option that administrators have is manual recovery. And administrators can spend significant amounts of time in this case and effort tracking down the attack's efforts as well as recovering from them. But even after spending so much amount of effort, administrators can still miss a subtle effect of the attack and not undo the attack completely. So this is the problem that we solve in this work. Our main contribution here is Warp, a system that recovers from intrusions in web applications. And during recovery, Warp undoes the attack as well as all of its effects while still preserving the effects of legitimate actions that were not related to the attack. Warp works for real applications like MediaWiki, Drupal, and Gallery 2. And in the rest of this talk, I'm going to present our key ideas: retroactive patching, which eliminates the need to pinpoint attack; time travel database, which precisely tracks causal effects of an attack; and DOM level replay, which preserves users' intended changes during repair. Our approach at a high level is as follows. During normal execution, Warp records the actions in the system to a log. It records the causal dependencies between these actions that happen in the system, and records and maintains checkpoints of system state. During repair, once the attack action is identified, Warp rolls back the system state which was affected by the attack to a time before the attack and skips the attack action and replays all the actions that were affected by the attack. By doing this, it effectively undoes the attack action as well as all of its effects while still preserving the legitimate changes. So let me illustrate this with an example. This is the same example as the cross-site scripting example, except it also contains the Warp state on the server side. During normal execution, Warp records the dependencies between the various actions in the system, represented here by arrows, to a dependency log. It also logs the HTTP requests and the database queries and the responses into a server actions log. It maintains checkpoints of the database so that it can roll back during repair. And finally, it records user actions such as keystrokes and mouse events using a browser extension on the client side. It records all of this to a client-side log, which is periodically uploaded to the server. So all this information that was collected during normal execution is used during the repair process. And to keep it simple, first I'll illustrate this repair process with a straw man, and then along the talk I'm going to refine different aspects of it. The first step in the repair process is to identify the attack action. In this case, it was Eve's initial request to the server containing the JavaScript code. Now, once the attack action is identified, Warp rolls back the database to the state before the attack and skips the attack action and replays all the subsequent actions. In this case, it replays Alice's subsequent requests. So re-executing Alice's actions includes Warp re-executing Alice's user actions such as mouse clicks and keyboard events. Since Alice might not be online while repair is happening, Warp launches a shadow browser on the server side and gives it Alice's client log to replay Alice's actions. Since the attack is no longer present, the database doesn't contain the attack code, so the response to Alice's request doesn't contain the attack code, and the attack requests don't happen, so we skip the attack requests. The shadow browser re-executes Alice's actions, and as a result of which the legitimate requests still happen, and we proceed to execute them. So at the end of this repair process, now we've canceled the attack action and all of its effects, while still preserving the legitimate actions that were done by Alice. To make this system practical, we needed to solve 3 challenges. The first step in the repair process is to identify the attack action. And identifying the attack action can be pretty hard. So that's the first challenge. And second, in the strawman repair example, after canceling that or skipping the attack action, we re-executed all subsequent actions. But many of those actions might not have depended on the attack action. So the second challenge is to reduce such unnecessary re-execution. Third, Warp needs to replay user actions while performing repair. And if a naive scheme such as a pixel-level replay scheme might not always work. And so the user might have to get involved to continue with repair. The third challenge is to reduce such user involvement during repair. The first challenge is intrusion detection. Differentiating between a legitimate request and an attack request is pretty hard, even for an expert administrator who understands the system very well. And normal administrators can easily miss such attacks. So to solve this problem, we propose the idea of retroactive patching. And the key observation here is that a patch for a vulnerability fixes the vulnerability. So if the patch was present when the attack originally happened, then the attack would not have been successful. So we use this idea to retroactively apply security patches back in time and re-execute all the requests which are affected by that patch. So this is how it works. During normal execution, Warp records for every request the script files that were loaded by that request. For example, in this case, it records the fact that Eve's request loaded main.php to its dependency log. And the repair process starts when the developer of that application finds a vulnerability, fixes it, and releases a patch. So let's imagine that the developer of this wiki server found the bug that Eve exploited in main.php and released a patch to fix it. Once the patch is available, the Warp rolls back the state of the system to a time at which the vulnerability was introduced into the system, and then applies the patch in the past. Then it proceeds to rerun all the affected requests. Since Eve's request loaded main.php, Warp re-executes Eve request. Now the wiki server does not contain the vulnerability, so the request is sanitized, and the database contains the sanitized input. When Alice's request is subsequently re-executed, and the response contains the sanitized input, so the subsequent attack requests don't happen, which we proceed to skip. So at the end of this retroactive patching process, we've made it seem as if the patch was present all along and the vulnerability was never present, and any attack which exploited that vulnerability in the past was made ineffective. And with retroactive patching, we don't need the expert to find the vulnerability, we just or the exploit. We just need the patch to clean up any exploits which happened in the past. So the second challenge is to reduce re-execution. Warp re-executes requests for two reasons. First, because a request depends upon an attack. In other words, the results of the request would be different if the attack was undone. And in this case, to reduce re-execution, we need a way in which we can precisely track dependencies between requests so that we can only re-execute the requests that were dependent on the attack request. And the second reason why warp re-executes a request is because of database rollback. So in the strawman repair example, once we roll back the entire database, we needed to re-execute all the subsequent requests to reapply legitimate changes. So to reduce re-execution then, we need to avoid unnecessary rollback in the database. Dependencies between requests arise because of reading and writing to shared state. And web applications store all their state in the database. So tracking these dependencies between these requests boils down to tracking dependencies between the SQL queries issued by these requests. We would like to have our dependency tracking to have two properties. First, we would like it to be precise, that is, to avoid false dependencies. This is important because web applications often manage many independent pieces of data, and we would like not to repair pieces of data that were not affected by the attack. And second, we would like our dependency tracking to be fast and track dependencies without having to rerun all the queries. And this is important because web applications often handle many independent requests, and we would like our dependency tracking mechanism to be efficient. So we can support either one of these properties, exclusively support either one of these properties very easily. So for example, we can have a whole table level dependencies, which is fast but not precise. In this case, we can say read on a particular table depends on all the prior writes on the same table. This is fast because by just looking at the query statically, we can determine what tables that does that query access. But this leads to many false dependencies because queries can access independent rows in the same table. So two queries which are independent would actually be marked as being dependent on each other. Another option is to re-execute reads after every write. So after a write happens, we re-execute every read and see whether the result of that read has changed. This gives us precise dependencies, but it's slow because it requires re-executing every single read. What we need is a way in which we can have a precise as well as a fast dependency tracking mechanism. And achieving this is pretty hard because queries name rows by different attributes, that is the columns in the where clauses, and queries do not specify every attribute. So for example, here if we see the update query is writing to all rows with a particular ID, and select query is selecting all rows of a particular category. And by just looking at them statically, we do not know whether those two, we cannot determine whether they depend upon each other, unless we know that there was one row in the table which had both the ID 5 and the category signs. So to solve this, we record the precise attributes to which the write writes to at runtime. So for each write, we record all the attribute values that it writes to at runtime. And for reads, we statically determine the dependencies based on the reads where clause. Note that doing that is pretty fast, and it's also very easy to do. So to illustrate this, with the previous example, statically we can, by looking at the update query, we know that it writes to ID 5, and we can see statically we can determine that the select query reads from category signs. And once the update query executes, we add this extra runtime dependency. Once we know that updated the row with category signs, we add this runtime dependency which to the category signs. And now we see that actually the select depends upon the update. Recall that our high-level challenge was to reduce re-execution, and I showed you how we can use precise dependency tracking to reduce the number of precise dependency tracking to figure out what are the requests that depended upon the attack to reduce the re-execution. The second thing we need to do is to avoid unnecessary rollback so that we don't unnecessarily re-execute requests to reapply legitimate changes. And our approach to avoiding unnecessary rollback involves two parts. The first part is to roll back only the affected parts of the database, only the parts of the database that are necessary for repair, so that we don't have to reapply changes to unaffected rows. And the technique we use this is to do a precise row level rollback. And the second part to this is to allow rollback to any point of time so that we don't roll back too far and need to reapply changes. The technique we use to do this is continuous checkpointing. So to implement this, we keep track of all versions of every row, and this allows us to roll back individual rows to any point of time in the past. And we add 2 columns to every row, which indicate the time interval within which that particular version of the row was valid. So for example, the row with ID 1 has 2 versions, one from a time interval 2 to 7, and the second from 7 to infinity. And indicating that the second version is the current version of the row. So Warp implements a time travel DB that combines precise dependency tracking of SQL queries and continuous row level checkpoints. Warp needs to re-execute user actions such as mouse clicks during repair, and a naive scheme like pixel level one naive scheme we can use is a pixel level replay of user actions, where we can click we can replay the click at the same location at which it originally happened. This pixel level replay scheme does not often work. For example, in this case, if the attack text was removed during repair and the whole page shifted, then user's original click on the button cannot be replayed on the same location. This results in what we call a conflict, and the user then needs to get involved during the repair process. We would like to reduce such user involvement during repair. The idea we use here is DOM level replay. And the key observation here is that DOM of a web page has structure as opposed to pixels. So changing one DOM element does not affect other unrelated DOM elements. Also, the DOM structure of a page represents the UI structure of the application, so the user's action on a particular DOM element more closely reflects the intent of the user. So for example, in both the required as well as the attack pages, the post button is the same DOM element with the same properties. So we implement DOM level replay. By normal execution, we record the user actions on the DOM elements. And during repair, while replaying a user action, we search for the same DOM element, and if it is not changed, we replay the user action. For text input elements, we additionally attempt to do a 3-way merge. If for any reason we cannot replay user action, we flag a conflict and queue it for later resolution by the user. So putting it together, Warp uses retroactive patching for initiating repair. It uses time travel database for reducing unnecessary re-execution, and DOM level replay to replay user actions and reduce user involvement during repair. We implemented these ideas in a prototype implementation of Warp. This prototype works with PostgreSDB, uses SQL query rewriting for implementing fine-grained row-level checkpoints. And it works with PHP and Apache, and we have Firefox browser extension that records user actions and does DOM level replay. In all, it's about 8,500 lines of code. Our evaluation of Warp answers the following questions. Can Warp support real applications and recover from real attacks? What does the administrator have to do to initiate a repair? What are the runtime overheads, and how long does repair take? The high bit of our evaluation is that Warp works for real applications. We've ported 3 real applications to run on Warp: MediaWiki, which runs Wikipedia software, Drupal, and Gallery 2. And for these applications, we did not need to change any application source code. We only needed to add a few lines of annotation for each table to indicate the columns for dependency tracking. To evaluate Warp's recovery capabilities, we picked 5 real vulnerabilities from MediaWiki and constructed complex attacks using those, which involve 1 attacker and 3 victims, where the attacker injects JavaScript code into a page, the victims visit the attack page, get compromised, and the attack code runs inside victims' browsers in the background, editing wiki pages, while at the same time, victims are also browsing and editing other pages. We have several other users in the workload who browse random wiki pages and make edits, but do not visit the attack page. In addition to these 5 attack workloads, we have one administrator mistake workload where the administrator gives admin privileges to a user who shouldn't have gotten those privileges. So the range of vulnerabilities which we explore here include cross-site scripting, SQL injection, CSRF, clickjacking, etc. And to initiate repair, we use retroactive patching for the 5 bugs. And for the ACL mistake, the administrator cancels the page visit on which he gave administrator privileges to the user. Retroactive patching, Warp can use real MediaWiki patches for initiating retroactive patching. So overall, the conflicts which we see during repair correspond to real attack side effects. For example, in the ACL mistake scenario, the user edited a page which required administrator privileges, and as part of repair, his administrator privileges were revoked, so we cannot replay those edits. That results in a conflict. Warp has about 25% throughput reduction in the server during normal execution, and anywhere between 3 to 7 kilobytes per page visit of logging overhead. For our workloads, for our applications, on one server at 100% load, this translates to about 1 terabyte disk storing 1 year's worth of logs. We measured Warp's repair performance for the workload that I've shown before. We measured the number of queries re-executed, the total number of queries, the repair time, and the original execution time. And overall, we see that Warp re-executes only a small fraction of the original execution, which corresponds to the repair time being an order of magnitude smaller. For some patches, we needed to rerun all the requests. So for example, the cross-site request forgery required the response to contain a token, so we needed to re-execute all the requests. And in this case, the full re-execution in our unoptimized prototype is an order of magnitude slower than the original execution. To measure how well Warp scales, we took a workload which is 50 times the original workload and measured the time to repair, keeping the number of victims the same. We see that it takes only about 3 to 9 times the repair time, which shows that Warp scales reasonably well. In related work, operating system level recovery mechanisms cannot be directly applied to web applications because they're too coarse-grained and they're inefficient for database recovery. The recent work by Akkas and Goel on web application recovery only recovers from accidental mistakes and corruptions, but does not recover from attacks. It also requires manual guidance to both find the attack as well as recover from it, or find the corruption and recover from it. Warp uses record and replay to perform repair, much like deterministic record and replay systems. But deterministic record and replay systems cannot replay once something in the system changes. Say, for example, they cannot replay the legitimate changes once the attack has been removed. Retroactive patching is similar to vulnerability-specific predicates, but vulnerability-specific predicates require a manual effort to write a predicate for each bug, whereas in the case of retroactive patching, the patch itself is the predicate. So in summary, I hope to have convinced you that intrusions are common in web applications, and administrators have very few tools to help them recover from these intrusions. We built a system called Warp that restores the integrity of a web application after an attack. Warp is based on a few key ideas: retroactive patching, time travel DB, and DOM level replay, and it works for real applications like MediaWiki, Drupal, and Gallery 2. We've shown in our evaluation that Warp recovers from a wide range of attacks that exploit real MediaWiki vulnerabilities. Thank you.
Fudan University. I have a question. What if the user's input is depend on the output of the web?
Of the browser, that's right.
Yes, the user input, because if the output is wrong, then user input may be wrong. But you cannot determine. You can change the output because you can replay, but you just receive the same user input, even if you replay.
Yeah,
right?
good question. So for the applications that we saw, the DOM level replay, the conflict detection mechanism that we have works well. And so it may not be applicable for all applications. In some applications, the user input might depend on the output itself.
Yes.
And the attacker can change the output of the function.
Yes.
So for those applications, we allow the application to write a conflict detection function, which will determine which are the important parts of the page and add to Warp's conflict detection capabilities.
Okay, thanks.
George Candea, EPFL. I think this is actually a follow-up question to that one, but I mean, it'll be obvious to any Star Trek fan. So what happens if you have external dependencies that are external to the actual timeline? So say I'm using this photo sharing site, and Alice, who I respect a lot, one of these attacks causes her to share her photos with everyone, and I look at it like, well, if she did it, I should probably share mine with her, but I would normally not do that. And now during the replay, there's this external dependency. There seems to be no way. So what are your thoughts on that? I mean, I know this is a hard problem, but you've thought about this a lot. So
the one approach, so the problem that is there is because the system doesn't have a way of tracking that external dependency.
Right, it's external to the universe.
It's external. It's in the user's mind, and like the user did something based on what he saw somewhere else. So in those cases, like one thing which you could do is give the user a way of figuring, once a repair happens, the user can go back and look at what repair happened and whether that repair would change any of the stuff that he did. So a way of auditing what the repair actually fixed. And potentially the user could then go and reapply and initiate undo for the other action which depended upon this action because of his own semantics of what he did.
So you'd basically like announce to the users we did a
yes.
Cool. Okay, thank you.
Previous question. Is there any attack vector opened up by the fact that you have this browser extension which uploads a bunch of stuff to your server which you then use in a replay? So I could imagine, I mean, I can modify the browser extension, right, and upload anything there. And then I assume that at some point you're going to be doing a replay. Can I somehow poison your web app that way? Or are you just going to drop my fake data?
Yeah, so very good question. So what we are careful in, when we rerun the shadow browser on the server side, we're careful to give it exactly what the user would have originally been able to do anyway. So that way we make sure that the user during the repair process can do exactly what he would have been able to do in the original scenario. But so the other part of the question here would be, should this user be able to even undo some of the things? And I mean, should the user be able to, because that affects other users potentially. And so in the current implementation or in the current design of the system, we allow the administrator to be able to undo most of the actions. And right now, user level undo is a future work for exactly that reason.
Okay, thank you.
Eric Ewell, Bell Labs. Just a quick question concerning how do you protect the warp data at the server? What if I attack that?
Oh, so currently warp data can be made read-only, so that it's logged off to a separate server, which is not accessible, and that server only appends to the log. Because it's a log, we can just append it and protect the log that way.
Okay.
All right, let's thank Ramesh again.